So, namaste, welcome back to another uh, uh, week of linear algebra through geometry. Uh, we are going to look into the next module, uh, which is basically on lines, parametric equation of lines in 2 dimension. We are going to look at the notion of linear maps. Basically, we are going to see how do we move in a 2 dimension, like what's the kind of transformations that we're going to have. So, we're going to look at linear maps. We're going to look at system of equations which you actually solved in the first and second module. That we are going to look at, revisit basically, and look at it in terms of vectors, and post that we are going to look at a very interesting idea for linear map, which we call as the eigen values and eigenvectors for a linear transformation. So, we are going to look at that. So, let us get going. I am quite sure in the previous module you all are aware that we did the idea of points and vectors, what differentiates a point and a vector. Then we looked at length of the vector, then we looked at the angle between vectors, we looked at orthogonality, we looked at inner product, we looked at projections and other things. So, in this module we are going to look at the following topics. Basically, we are going to look at lines and equation, lines in 2D. Basically, we are just going to focus on the parametric form of lines in 2D, and that is essential and interesting because we will see that when you solve a system of equation, we would actually be doing parametric form of line. We will look at that, which comes from the idea of the total solution to the complete solution to the system of equations. Linear equations is basically you would look at it as the particular solution plus the scalar multiple of a homogeneous system of equation, which basically defines the geometry there. So, we are going to look at that. So, we are going to look at parametric equations of line, parametric equation of lines, followed by we are going to look at linear maps in 2D. We are going to look at or revisit linear systems of equation, let us say linear systems 2 by 2, systems 2 by 2. Then we are going to look at eigenvalues and eigenvectors in 2D, eigenvalues and eigenvectors in 2D. In 2D. So, the question is, what is it to say parametric form of line? So, what is a line in the first place? We looked at that in the previous lectures, where we basically looked at the idea of a point. If you recollect, we had a point P, and then we had another point Q. We had a point P and we had a point Q. We had a point P and a point Q, and we said that Q minus P, which is basically Q1 Q2 minus P1 P2, which basically gives me Q1 minus P1 and Q2 minus P2. We called this as a vector R. We said this is the vector R, which is given by Q minus P, and we said if we want to move from, let us say, to move from P to Q, we said we did the following. We basically looked at P plus, let us say, some scalar times K times R, where P is the basic point, which is P1 P2. We said that you go along the direction of the R, basically R is the vector, and we said you go along the direction of R, where K is some scalar, K into, let us say, this vector R1 R2. Now what we are trying to do is we are going to look at the idea of let us say parametric equation of line. So what is it to say parametric equation of line? That is going to be a very interesting topic, as I said before, for the simple reason that it's going to help us understand the notion of lines, and through compact form. I mean, they understand the idea of lines through a compact form, where we are going to write equation in the form. Okay, let us do that. So first of all, so what is a line? Basically line, so we are going to look at line as basically let us say 2 points. I mean, if we could say that 2 lines. Okay, let me make it this way, sorry. So let us do this. We have 2 elements of a 2D geometry, 2 elements of a 2D geometry basically define a line, defines a line. That is the simplest geometry that you can fit between 2 points. So the first one that we are going to look at is basically 2 points. 2 points define a line between them, 2 points. Then the second one is a point and a vector parallel to the line, and a vector parallel to the line. Or the third one is basically a point and a vector perpendicular to the line, point and a vector perpendicular to the line. So we get into the idea of this parametric equation of a line. What does it that a parametric equation of a line, what does it actually mean, right? So suppose I have a function, like I have L of t, which basically defines the line. This is basically given by P, a point plus a scalar times V, this vector, where t is basically, say, some scalar. I am sure okay, let us write this. T is basically the parameter that we are looking at. T is basically the parameter. Okay. We also remember that this vector V can be written as q minus p. Recall, vector V can be written as the points p minus q. Let me let us say q minus p, and we figured out that in terms of the barycentric notation, we said that barycentric coordinates, we said that the line L of t, you can write this as 1 minus t times p plus t times q, and we also I mean, this is also called as a parametric equation of line, and this is also called as a parametric equation of line. And we said that if t is going to be a value between 0 and 1, we call that to be a convex combination, and a lot of other things that we did. If t is going to be less than 0, okay, let us write that. So if 0 less than t less than 1, we call that as and we call that as the convex combination. Then we are going to say t less than 0 or t greater than 0 or 1, we are going to do what is known as extrapolation between the extrapolation. That means in case of convex combination we get the points in between the 2 points p and q, whereas in this case we are going to get the values which are beyond p and q. I hope that is fine, right? Okay. So, now what do we do? Where do we go from here? So, let us just take a simple example and probably look at if we are able to make sense out of this. Let us just take a simple 2 by 2 system example, which all of you would have done in the previous module. Let us take 2x1 plus, let us take an example, 2x1 plus x2 is equal to 3, and let us take 4x1 plus 2x2 is equal to 6. Now, we all studied the idea of homogeneous system of equation. Homogeneous system of equation that corresponded to say 2x1 plus x2 is equal to 0, 4x1 plus 2x2 is equal to 0. This is what we have, and we know that the solution to this lies along the line through the origin and the point (1 minus 2). And we know that if the homogeneous system of equation has non-trivial solution, we studied that has a non-trivial solution, then it has infinitely many solutions. Infinitely many solutions. So, for example, in this case we said that 1 minus 2 is a solution. Now, what we are going to say is the scalar multiple k times 1 minus 2 is also a solution to 2x1 plus x2 is equal to 0, 4x1 plus 2x2 is equal to 0. And you keep changing the value of k basically say some real scalar, you keep changing the value of k, you end up getting infinitely many solutions. Now, suppose I want to solve this from here. Let us look at the non-homogeneous system of equation. 2x1 plus x2 is equal to 3 and 4x1 plus 2x2 is equal to 6. We know that x1 is equal to 2, and okay, let us look at that. So, what is the solution for this? What is the solution for this? So, we are going to have x1 is equal to 1.5, x2 is equal to 0 is a solution, x1 is equal to 1, x2 is equal to 1 is a solution, x1 is equal to 0, x2 is equal to 3 is a solution, and so on. So, we see that even this non-homogeneous system of equation has infinitely many solutions. So, if you want to look at the total solution to this given system of equations, the complete solution, let me call that as the complete solution, complete solution to 2x1 plus x2 is equal to 3 and 4x1 plus 2x2 is equal to 6 is basically is given by x is equal to xp plus k times xh, where xp is a particular solution to the given right hand side, particular solution, and xh is the solution to the homogeneous system of equation. Right. So, if you look at this, you keep changing the value of k, you basically get onto a set of points which appear on a line which seem to be the solution for this system of equations. So, that is exactly where we get into the idea of parametric parametric form or parametric equation of a line, right. Now, so in essence we just want to look at the structure of the what do you call the structure of the solution to a given system of equations, and the structure of given system of linear equations can always be expressed, or the complete solution to the system of equations can always be expressed as particular solution plus a scalar multiple time the homogeneous system of equations, the solution to the homogeneous system of equations, and that looks like a parametric form of if it's going to be a 2D, it's going to look like an equation of a line. Yeah, okay. Now, having seen this, what are we going to look at? We are going to look at the idea of with points. We just saw that we could construct lines and other things. Now, so in any geometry that you take, the first thing is like about construction, and the second thing is about transformation. So, we are going to look at slowly move from the idea of construction to the idea of transformation, where we are going to look at linear maps. Let me write that as linear transformations. Linear transformations of vectors in 2D. Now, what do we mean by linear transformation, and why are we even studying this? These are things that will form the next couple of topics that we are going to look at. So, let us get on to what this linear transformation actually mean. Okay. Okay. So, let us take a simple vector. Let us take consider so let us do this. Let us get to the notion. So, what are we going to do? We are going to say that so in geometry we typically focus on two things. We focus on a description of objects that can be generated, focus on describing objects that can be generated, and B, we can look at how these objects focus on changing these objects or transforming these objects. So, in this particular topic we are going to look at how to transform these objects, that is what we call as linear transformation. Okay, let us take a simple example. Consider E1 to be this vector, let us say 1 0, and E2 to be this vector, let us say 0 1, right. Now what we are going to do is, I want to generate a vector V. Let us do this. I want to generate a vector V which is nothing but, which has components, let us say V1 and V2. Now how do I generate this vector? This can be easily generated as V1 into 1 0 plus V2 into 0 1. Essentially what it means is V1 into E1 plus V2 into E2, right, and where now V1 turns out to be a scalar and V2 turns out to be another scalar. So we basically get the vectors 1 0 and 0 1, they get mapped to the vector V1 V2 when you take these values of V1 and V2, right. This is something which we know. For example, if we take the vector V, which is basically given by 5 4, I can write this as 5 times E1 plus 4 times E2. This is pretty straightforward and simple, so we can do this, right. But what is interesting is, like, how are these E1 and E2 axes, where are they? Let us look at that. So we are going to have this, we are going to look at E1, which is basically this vector is E1 and that vector is basically E2. We said this is 0 1 2 etc., and we are going to call this a 0 1 2 3 etc. So we are going to have this E1 axis and E2 axis, where we have the idea of any vector, we have got any vector in this 2 dimension can be generated as a linear combination, which we have studied. So any vector V can be expressed as V1 into E1 plus V2 into E2. That is, we express the vector V as a linear combination of these two vectors E1 and E2. Okay. Now is this all we can do? No, we can actually we can take any two vectors. Say for example, in this case, if you look at it, this vector E1 and E2, I can do the same business like what I did the other time, where we can draw this E2 perpendicular, I mean at the head of E1, and I can draw this E1 at the head of E2, and then I get a unit square form. This is basically my unit square. So the area is 1 because this is of length 1 and that is of length 1. So the area is basically 1 here. So now what we want to do is, we want to express, let us say we can actually look at, why do we want to even look at E1 and E2? Why not we just take any other vector, let us say A1 A2. For example, let us take this, let us take this vector and let us take some other vector. Okay, let us take this vector to be, okay, let us draw this again. Suppose I take this, vector 2 1, which is basically in this direction, and I take this vector 1 2, which is basically in this direction, right. This is 0 1 2 3 4 5 6 1 2 3 4 and so on. So this vector is basically, I will call this vector, let us say u as 2 1, and I call this vector v as 1 2, right. Now what I want is, I want to express, let us say I want to express this vector, which is like say w, which is given by 3 3, as let us say the linear combination of k1 of the vector u and the vector V, right. We want to figure out what is this. I mean, can we express this vector 3 3 as a linear combination of these two? That means we need to find out the scalars k1 u plus k2 v. We need to find out the scalars k1 and k2 such that you get 3 3 as a linear combination of the two vectors, right. So, it is very it is not difficult to see that k1 is equal to 1 and k2 is equal to 1 will help us get 3 3 as a linear combination of 2 1 and 1 2, right. So, if we want to write this, so we can write this. So, we can capture the linear transformation of a vector in a matrix form. In a matrix form. Now, how do we capture this? For example, we wanted this vector 3 3 to be written as k1 into 2 1 plus k2 into 1 2. So, what we see here is I can rewrite this as 2 k1 plus k2 is equal to 3 and k1 plus 2 k2 is equal to 3, right. This is again a system of linear equations which we have seen before. So, I am going to write the coefficient matrix as 2 1 1 2 and we are going to say that 2 1 1 2 transforms this vector k1 k2. It acts on these vectors k1 k, the vector k which is given by k1 k2 and going to give me a vector which is 3 3, right. That means this maps the vector k which is equal to k1 k2 to the vector which is 3 3, yeah. So, what we do is we can actually that is exactly what we have been doing. We are going to look at capturing the linear transformations in the form of a matrix. For example, if we have A11, A12, A21, A22 into let us say the vector x which is given by x1, x2, we are going to get another vector which is A11 x1 plus A12 x2 and A21 x1 plus A22 x2, yeah. So, what is this what is the transformation trying to do? The transformation that you have here is going to map this vector x1 x2 to the vector which is given here, yeah, okay. So, what are the different transformations that we want to study? We will look at all that, okay. We will look at what are the different transformations that we are going to study. Some linear transformations on vectors in 2D. The first most important thing that we study is like we are going to focus on, let us say scaling a vector, scaling operation, look at scaling a vector. Now, what does it mean to scale a vector? Say suppose I have a vector v which is given by v1, v2 and this vector has to be transformed to another vector, let us say k v1 k v2, where k is say some scalar. Now, how do we capture this transformation through a matrix, right? So, we are going to look at that. So, what are we going to do? I am going to say that let us say I have a matrix, I do not even know what that matrix is. I have a matrix which is let us say A11 A12 A21 A22, and this transformation acts on this vector to give this vector which is k v1 k v2, which means it is easy to see that we have A11 v1 plus A12 v2 is equal to k v1 plus 0 v2. Similarly, A21 v1 plus A22 v2 is equal to 0 v1 plus k v2, and if you compare the coefficients of v1 and v2 in each of these equations, we actually get the matrix which scales. So, the matrix that does or the which does the scaling is basically given by k 0 0 k. So, this acts on this vector whose components are v1 and v2, and we get k v1 k v2. That means, depending on the value of k, you will see that if k is more, the vector gets elongated, the vector gets elongated. If k is between 0 and 1, then you say that the vector is like contracted, and if k is 0, you are going to get to the 0 vector, and if k is negative, you are going to basically go to the opposite direction. Yeah, okay. So, what does it do? Let us just take an example. Let us say I have this vector, I have this vector 2 1, and I want to scale this vector 2 1 so that I get 4 2 through this matrix. So, the 2 1 vector basically gets scaled by this matrix to give you 4 2. Yeah, okay. What is interesting to see is, if let us consider this unit square where we had this, the unit square is basically 0 0 0 1 sorry 0 0, and this vector is basically 1 0, and this vector is basically the 1 1 vector, and this vector is basically my 0 1 vector. Yeah, that vector, let me call that as E2, let me call this as E1, this is E1, this vector is basically E1 plus E2. Now, we saw that the area of this unit square is 1, area of unit square suppose I scale, let us say I scale this unit square, I put all the coordinates of this and then scale it using this. The coordinates of the square are 0 0 1 0 1 1 0 1. So, we are going to get 0 0 2 0, this is 2 2, and that is 0 2. So, which means our new object that we get is basically here. So, you have this is 2 0 and that is 2 2 and this is 0 2. So, you see that the area of the square changes, that means the scaling transformation affects the area of the object. The area of the object that scaled. Right? Okay. Okay. So this is the effect of scaling. So this is the first linear transformation that we have studied. We'll look at the next one, which is basically the idea of reflections. Reflection transformation is what we are going to study. Now, what is it to say reflection? How do we understand this idea of reflection? For example, I have a vector whose components are, let us say, v1, v2. We all know that in reflection, when you go stand in front of a mirror, we see that the left appears right and right appears left. So basically, reflection just corresponds to, in this case, it corresponds to swapping of the rows. In 2D, reflections in 2D, what we see is this is basically swapping of the rows. So I want to get that transformation. What is that matrix transformation, or what is that transformation which will I mean whose matrix representation will swap the coordinates of the vector. So how are we going to do this? We will go to the same thing. We have A11, A12, A21, A22 into V1, V2 gives me V2, V1. You can actually again write the set of equations. You get A11 V1 plus A12 V2 is equal to 0 V1 plus V2. Similarly, A21 V1 plus A22 V2 is equal to 1 V1 plus 0 V2, which means the matrix that reflects. So reflection transformation, the matrix representation is given by 0 1 1 0. So what are we going to say? In fact, if you may recall that when we did elementary row operations, we did row swapping, elementary row operations of row swapping is done by this matrix, is carried out using this matrix. The matrix 0 1 1 0. And it is also interesting to see that once you have reflected, you want to get back to the same coordinate V1, you want to get back to the original coordinates, which is V1 on V1 V2. All you need to do is you need to swap this resultant vector again with the same matrix, which is 0 1 1 0, which means in order to undo the operation that is done by this matrix, you apply the matrix again, right. So what we do is we say this, in order to undo the effect of swapping, apply the same transformation again. Which means in essence, this matrix that you have for reflection transformation, let me call this as the matrix R, that matrix is its own inverse. That is another way of saying. So, we are going to say this, the inverse of reflection matrix R is R itself. Now, let us see what actually happens. What happens, say for example, I have let us say I have this vector, let us say 3 1, this vector I call this as the vector u is given by 3 1, and I apply this matrix 1 0 1 1 0 on 3 1. This transformation results in 1 3, which is basically this 1 3 is here, and what the matrix does is basically the following. The matrix reflects all the points about the line y is equal to x, or suppose if I take this as x1 axis and that as x2 axis, then it reflects about x2 is equal to x1 line. Okay, so what have we done? We, in this lecture, we started off looking at the parametric equation of a line, and we connected it to the complete solution for the system of equations, where we had the idea of particular solution plus the solution to the homogeneous system of equation. And then we started looking at transforming objects, and we were trying to capture the idea of transformations through matrices, and of which we looked at 2 of these linear transformations, namely scaling and reflection. We have some more. So, what are the other transformations, linear transformations that we can do? Is there something interesting that we can? So, what are the are there any other linear transformations that we can do, standard things that you have? So, let us ask these questions. So, are there any more linear transformations? How to invert? I mean, can we let us do this, can we reverse the effect of a linear transformation? These are the questions that we will take up in the next lecture. Thank you.